You are welcome to the lecture series for EE771 Digital Signal Processing. And let us start discussing the subject with the definition of signal, as we are going to learn the science of processing the digital signal. So we need to understand the term signal in general as well as in detail. So a signal is a function. A signal is a function giving some information. This function will have several dependent parameters or several parameters on which the function is dependent. There can be a function which depends on a single variable, or there can be functions or signal that depends on many or multiple variables. Say if I represent a signal as x of t equal to 2 times sine 2 pi 50t. It's a 50 Hz signal varying with respect to time t. So it has a dependent variable t, and that's why it's a single dimensional signal. Now take the case of a signal which has form 2 sine 2 pi 50t into resistance R varying with respect to the temperature. So here my signal is dependent on two of the parameters, time t and temperature. Because of the variation in temperature, the resistance changes, and with respect to time also the signal is varying. It means now signal is dependent on two parameters, t as well as temperature. So such a signal can be considered as a 2D signal. Say I have an image. Image is nothing but set of information given in the pixel in form of pixel. Now these pixels are located with respect to the x coordinate and y coordinate. So information at each of the x and y coordinates is varying one, because informations of pixels are different, representing a complete picture. So the information present over here is dependent on two of the parameters or two of the coordinates x and y, and that's why this is also an example of 2D signal. As a power system engineer, you will be mostly dealing with the signal of one dimensional. Say for example, you want to develop a numerical relay, and for the same you are collecting the information from the current transformer. You are deriving the analog signal from the secondary of current transformer or the potential transformer. The secondary signal is varying with respect to time, and that information is in analog domain that needs to be converted into the digital for processing by the digital platform. So as signal is varying with respect to the time, it can be regarded as a one-dimensional signal. So now this analog signal or this signal can be of two types: analog signal and digital signal. Analog signal can again be classified into two: continuous time signal and discrete time signal. But the digital information or digital signal cannot be a continuous signal. It is always discrete time in nature. So what do we mean by these two terms, continuous time and discrete time? Say for example, if I have a signal of 50 hertz like this, it's a sinusoidal signal and it's of 50 hertz, so duration of cycle is 20 millisecond. Of course, if I want to represent the signal with zero errors, I will need each samples present into it, and you will appreciate that there are infinite numbers of samples, infinite numbers of samples present into this signal. Signal available at zero time, signal available at 1.0000001 millisecond, signal available at 1.000000001 millisecond, and so on. So ideally speaking, if I want to draw this signal without any error, means with zero error, I need to have information of infinite numbers of samples. Even if you take any two instants over this signal, say T1 and T2, then also to describe the variation of the signal between these two time instants, you need to have information of infinite numbers of samples. Is it possible to have knowledge of infinite numbers of samples? Is it possible to store infinite amount of data? Is it possible to process infinite numbers of samples on the digital platform like microprocessor or microcontroller or digital signal processor? Not, of course. You know it. The microprocessor or microcontroller requires a clock signal, and with each clock signal or machine cycle, the instructions are processed, and program is collection of instruction, and that's why processing a mathematical equation or processing a set of digital information requires finite duration time. So if there be capacity of storing the infinite numbers of samples, which is really practically not possible, but let's assume it for the sake of discussion, then also the DSP or microcontroller will not be able to process it in the real time, in no time. Means continuous time signal are not fit to be processed by the digital platforms, right? And there are of course reasons why The world is moving from analog domain to digital domain. Let us not discuss all the advantages of having digital counterparts over the analog counterparts. You know it very well, and you will appreciate that it cannot be processed, means a continuous time signal cannot be processed by processors like DSP or microcontroller. So what we really need is we need to convert a continuous time signal into the discrete time. And yes, you have guessed the correct definition or look of the discrete time signal. Discrete time signal is defined for several of time instants only. Say, I want to describe the signal as set of 10 or 12 numbers of sample. Those 10 or 12 numbers of samples may be like I am showing over here. So this is my first sample, this is my second sample, third, fourth, fifth, sixth, seventh, eighth, 9 and 10 samples. These samples are generally taken at regular rate called TS, sampling duration, which is inverse of sampling frequency Fs. And as the signal is defined at several distinct moments of time only, it is called discrete signal. So now, instead of infinite numbers of sample, signal is represented by the set of finite numbers of samples, and that's why a memory available with the DSP or microcontroller can store it and can process it within real time. When I say real time, it means it can be completed, the process can be completed in a given time boundary. So depending on the requirement of the processing time, you will need to choose the processor either, or you will have to lower down the numbers of samples. So now we have some idea about continuous time signal and discrete time signal. Let me put it other way. A continuous time signal, as we have discussed, has a variable t, and it varies with respect to the time. The signal can be defined by set of infinite numbers of samples, or we can say that there are no samples but signal is continuously varying with respect to the time. Now if x of t is given by 5 sine 2 pi 50t, and of course it is a continuous signal. It can be written in form of mathematics with the variable small n like this, representing its discrete version. 5 sine 2 pi 50 into instantaneous time is given by n into ts. So here n is an integer variable, like n can be 0 or 1 or 2 or any integer number. So suppose I start the sampling process, then n will be set to 0 and I will have a sample called x of 0. Then after ts time, I will again take a sample. Say I am sampling with the sampling frequency fs equal to 1 kilohertz. Then ts is 1 over 1 kilohertz, that is 1 millisecond. So after 1 millisecond, I will be again taking the sample. So x of 1 millisecond can be written as 5 sine 2 pi 50 into 1 millisecond, or it is n into ts, that is 1 into 1 millisecond. Similarly, again after 1 millisecond, if I define the signal, if I find out the signal, then it is nothing but x of 2 millisecond equal to 5 sine 2 pi 50 into n. Now n is equal to 2. So 2 into ts is 1 millisecond, of course. So it will give me the strength of signal at 2 millisecond. So this is a correct way to represent a continuous time variable t as a discrete time t. So discrete time t discrete can be given by small n into sampling interval ts, where n is an integer. So this is how a discrete signal can be mathematically defined. For defining the discrete time signal, you will need to replace a continuous time variable t by a discrete time variable t. Now, let us understand the process of converting the analog continuous time signal into the analog discrete time signal, and then it can be converted into the digital information that can be processed on the platforms like DSP. So we are going to talk about basic building blocks that you will able to see in any digital processing, digital signal processing system. So at the front end, you will have, or you have, a transducer, a device which can convert the quantity being measured into the electrical signal. Of course, this is an analog signal. It's a continuous time signal. So let me represent it as x of t. Okay. Now I want to convert it into the discrete time. So as we have discussed, I need to sample, I need to collect the information of the signal at various instant of time. So I need to evaluate the signal, I need to collect the information of signal at moments separated by the sampling interval Ts. So such a hardware block will require sampling impulses. The sampling impulses will look like this. So it is a triggering signal, and basically whenever this triggering signal is available, you will have output available which will be equal to the input at that moment of time. So here you have a continuous time signal, right, x of t, and you are converting it into the discrete time signal x of nt. Now before you apply the output of transducer to the input of this circuitry, which is a sampler, you need a block, another block called anti-aliasing filter. And we are going to shortly discuss about it just after completion of the basic building block of the digital processing system. Now, as this is a discrete time signal in the in the analog domain still, we need to convert it into the digital, and for the same you will require a block called analog to digital converter. But is it sufficient to apply the signal to the input of analog to digital converter? Let us try to understand. Say this is a continuous signal. I want to convert into the digital. So I can sample it over here. After 1 millisecond, I am again sampling it over here. Again after 1 millisecond, I am deriving one more sample. Again after 1 millisecond, I am re-deriving the sample. So there are certain set of samples representing this signal. In between the two sampling instants side by side, the signal x of nt is 0 because this is just an impulse. The output of the sampler will be available for a moment only. So in between the two sampling instant, the output of sampler is strictly 0. So this impulse is of the magnitude or amplitude equal to the input signal x of t are available at various instants t1, t2, t3, t4. Each successive time instants are separated by ts duration. So suppose this kind of pulse train is given to ADC, analog to digital converter. Will it be able to convert it into the digital information? Not, of course, because it needs some time to convert any given signal into the digital one. Say the conversion time is 0.1 millisecond. So the signal available at 1 millisecond, the impulse available at 1 millisecond should be at least holded for next 0.1 millisecond duration, means up till 1.1 millisecond. If it becomes 0 before 1.1 millisecond, the ADC will again have 0 input, and that's why the process which was initiated at the moment t equal to 1 millisecond will fail to tell you about the strength of the analog signal, the digital equivalent of the analog signal. So we need to hold it, and it is even better to hold it up to the next sampling instant, so that even if ADC take more time, then also that signal will be available to it. So we need to hold this signal up to the next sampling moment, and if we do so, the signal will look something like this, right? So this is the kind of signal available with the holding circuitry, sample as well as hold circuitry. So sampler alone is not sufficient, and along with the sampler we also need a hold circuit. Combinedly, we say that we need sample and hold circuitry before we apply the discrete time signal to the ADC. Output of ADC is digital information, and that's why a DSP processor or a microcontroller can pull this information and can put the information into the memory. So here we have a fast processor. It should be at least fast, that can give you, that can compute the processing, that can compute the processing equations within allowable time. The speed of this processor is tremendously fast, and generally it is given in either of the three units: million instructions per second, mega floating point operations per second, or tristan million instructions per second. So here we need to code for the discrete system required for processing the discrete time or digital signal. You may also require to convert it back. You may also require to convert the digital signal back into the analog signal. And in that case, you will need a block called DSC, digital to analog converter. The output of digital to analog converter will be of kind discrete analog, and hence let me represent it as y of n into ts. So this will have form similar to this. So suppose I have a mic as a transducer and it is converting my voice signal into the electrical. I am converting it into the discrete time signal using sample and hold circuitry, and then I am converting it into the digital information using analog to digital converter. Then I may need to suppress several harmonic using the digital filter. So algorithm, that digital filter will be implemented or will require to be implemented on the platform of DSP processor. Now, as this is a music signal, your application may also need to convert it back into the analog, because you may also need to hear this signal again. And signal can be played on the device like speaker, and speaker accept the analog signal, and that's why this digital information after filtration needs to be converted into the analog signal. So discrete time analog signal that will be available as output of digital to analog converter will look like this. It will have abrupt jump, sudden jump at the sampling moment, at the moment when digital information is updated at the input of digital to analog converter. As soon as you change the digital information given to digital to analog converter, digital to analog converter will change its output as per the given digital information. So these are the moment when digital to analog converter will change its output suddenly. Now this sudden change in signal actually represents presence of high frequency components at this time moment. And if you play such a music signal on the speaker, the sound quality will be really too bad. So you need to suppress this harmonic. You need to suppress this abrupt jump, and you need to make it smooth. Instead of signal like this, you should smooth it out like this. So what you can do is you can use a filter here, a low pass filter can remove the high frequency harmonic present in the signal and can make it smooth. That will give you better quality output. So the figure you can see here covers several blocks that you can find out in any digital signal processing system. But please remember that not all the systems will have all the blocks. Say for example, if my application is playing some audio from the recorded version of the song, then recorded version of song may be available inside the CD or DVD. So DSP processor will directly read those digital information. So why to have this block ADC, sample and hold, anti-aliasing and transducer? You don't need it. You can simply skip it. But if your application is deriving the music information from the mic, you will need all these blocks. Similarly, if your application is just to record this signal, you will not require to convert it into the analog, and you can skip DSP reconstruction filter. This is called reconstruction filter. Okay. You will not need reconstruction filter or speaker. But if signal is to be played on the device like speaker, you will need it. Suppose your application don't need to play music signal. It may be a numerical relay. So numerical relaying, maybe let's take an example of numerical overcurrent relay. So what is the function? The relay will measure the RMS quantity of the current of the relaying signal. So current transformer will serve as a transducer, and secondary output of current transducer will be given to analog to digital converter via certain block we have already discussed. Of course, we still need to discuss about anti-aliasing filter, and we'll be discussing it shortly. So you will be converting it into the digital, and those digital information representing the signal will be processed for digital RMS. That will be done by the digital signal processor. And if RMS calculated will be higher than certain value, certain threshold value, we say pickup current or pickup setting, then DSP processor will trip the circuit breaker via certain mechanism of NONC contacts and tripping coil. So there you will not need digital to analog converter, reconstruction filter, speaker, etc. So depending on the application, several of the blocks may be present or absent. But these are the components you will generally find in any of the digital processing system. So now you know several things. You know several basic things about the signal. You know from where signal is coming, what is the role of sample and hold circuitry, what is the difference between a continuous time signal and a discrete time signal, why digital information or digital signal cannot be a continuous time signal, or equivalently why a continuous time signal can't be processed on the platform of digital signal processor, how a basic building block of a DSP system will look like, and what is the role of individual blocks in it. You know it very well. You also know how to convert the given mathematical form of continuous time signal into the discrete time signal. So now it's time to discuss several examples of DSP processing. Let's discuss several basic examples, like how to discretize the continuous time integration into the discrete time integration, how to convert continuous time differentiation into the discrete time integration, and so on.